This video is going to cover the topic of linear relationships. Be sure the date and topic are at the top of your page. The essential question of this video is, what are linear relationships and how are they represented in graphs, tables, and equations? And we'll start by defining the term here, linear relationship. So the formal definition of linear relationship is one where there is a constant rate of change between two variables or two quantities. And that means that the rate is proportional throughout the entire relationship. And a non-formal way to think about it is that that is steady, right? So if something's happening and it costs $5 for every pound, then the next pound would also cost $5, and the next pound would cost $5, and so on. So in our first example, we'll say that Piper can walk 9 meters in 3 seconds, right? So we want to figure out, of course, first, how far she can walk per second. And I'll do that by dividing her meters by her seconds, and I'll find out that she can walk 3 meters per second. And we're going to assume for this example that Piper continues at a constant rate, always walking the same speed. That means she doesn't speed up and she doesn't slow down, she doesn't stop or start running. So she's going 3 meters every second that she walks. And we're going to represent her speed in 3 different ways. The first way is with a table. So we're going to make a table that uses the 2 quantities in her ratio, time and distance, how far she can go and how long it takes her. So my table has the 2 quantities, right, of her ratio, time and distance. And let me just remind us that she is walking 3 meters per second. So that means, of course, that if 0 seconds pass, she won't go anywhere. But after 1 second, she'll go 3 meters. After 2, she'll go another 3 meters for a total of 6. After 3, we'll add on another 3 meters. After 4, she'll go another 3 meters, and so on. Right? And this would continue. This is considered linear because the time is increasing at a consistent rate, right? We're going up by 1 every time, 1 second extra. And the meters are going up consistently by 3 every time we add on a second. I'm going to show you a non-example here that's not linear. So let's say that Piper starts off at 0, walking no distance, and after 1 second she has gone 3 meters. After 2 seconds, she's gone another 3 meters, but then she stops and she stays at 6 meters, and then she starts up again but goes a little bit faster and goes 4 meters in between, and then she slows down a little bit and on her last turn only goes 1 extra meter. This would be non-linear. And this is non-linear because every time my second goes up by 1, right, it's nice and consistent, the number here changes. This went up by 3, this went up by 3, but then in 1 second it didn't go anywhere. In another second it went up by 4, and in the last second it only went up by 1. If I were to find the unit rate for each of these, they would not be the same. It would not be consistent. So that's what we can see when we look at it as a table. Let's look at a graph now. We can graph this as well, and we're going to do a graph of her time versus her distance. We know that she's going 3 meters per second, which means her meters, how far she goes, depends on how much time she has. So that means time is just going to keep passing and is our independent variable on the x-axis. And from here, I'm going to plot her points, right? So at 0 seconds, she had gone 0 meters. After 1 second, she had gone 3. After 2 seconds, she had gone another 3, getting her up to 6. After 3 seconds, she went up to 9. And after 4 seconds, she went up to 12. So I've plotted her distance on this graph. And something to notice is that as we graph it, if I were to connect this, it would make a straight line. Right? And I don't have a ruler here. We would use a ruler in class if we could, but I can't use a ruler on this application here. But what we want to notice is that when something is linear on a graph, it forms a straight line. This is proof of a linear relationship. If this were not linear, the points might be all over the place and it would not make a straight line, and that would be how we know it is not consistent. Lastly, we can create an equation that shows how fast Piper is walking, and since the relationship is constant, this won't be too terribly challenging. So as we know, she walked 9 meters in 3 seconds, but we know that that was 3 meters per second, and I can use a variable to write this equation to show how far Piper can walk. So Piper's distance is 3 meters per second. So we can translate this into an equation. D for distance is equals 3 meters times every second that she walks. So we can find her distance regardless of her time. So if she walks 10 seconds, we could substitute that in and say her distance is 3 meters times 10 seconds, right? Which of course would mean her distance is 30 meters. If she walks for 20 seconds, then we would say her distance is 3 times her 20 seconds of time. So her distance would be 60 meters. And in that way, we can translate this into an equation. And when something is linear, we look for that unit rate, right? Her original 3 meters per second, and that will give us the coefficient in our equation. You'll have just one more thing to do here before our video ends, and that is to decide if something is or is not linear. So we have here 2 people and their walking rates. We have George and Elizabeth, and your job is to decide, you can check off the boxes at the bottom, which one is linear and which one is not. One of them is walking at a consistent rate. It is proportional every single time. The ratio is the same, and the other one is not. So take a moment and see if you can decide which one is which. And remember that the essential question of the video is, what are linear relationships and how are they represented on graphs, tables, and equations? Be sure to bring your notes and any questions you have to class.